Okay, so yeah, I think I've started recording. Uh, Now let me just go to. Hmm, I'll share my screen. So now, hmm, I'll give me 1 second. Hmm, I'll just make a. So this is the. So I'll make the introduction slide till people are coming in. So yeah, what I'll do, I'll just see what we did last time. Okay, so this is week 3. So I'll write here week 3 assignment discussion. And yeah, so I think then I'll just, since these slides will be shared, so I'll put my my name and all for yeah. So yeah, I think it's about time. So we wait for some time to people to join. I think Narendra is here. Hello.
Hello, sir. Hello.
Narendra, are you able
Uh,
to hear me?
yeah, sir. Good evening, sir.
Good evening. You are not there in last class, Narendra. What happened?
Actually, I was out of station, sir. I
Oh,
tried to join, but it was not held.
okay, okay. No issues. No issues.
I was at Nagpur for
Why?
for some work.
Okay, okay.
Mm.
Yeah, yeah. Actually, I thought you got disinterested and left the classes maybe.
Just now I have seen the recording of last any live session, your live session.
Okay. I hope that
Mm.
was some of it was helpful.
Useful, sir, and definitely.
Yeah. So today also we'll cover the week three assignment or the topics related to week three.
Mhm.
I hope you had time to see the lectures online, NPTEL lectures. If not, it's fine. I'll just briefly tell you what it is all about. Maybe then you can go back and refer.
Mm.
But let's wait for some time. For
Okay,
like
sir.
2-3 minutes, we'll wait. We'll start at 6:05
Mm.
because people join late and then the session gets extended. And also, better to start early. Let people join whenever they are, like they are coming. So we'll wait for 3 minutes. Then we'll start. Okay, Narendra.
Okay. Okay, sir. Sir, may I ask one doubt regarding the assignment two?
Tell me.
Uh, Actually, that that there was a question, known question. You
Mm-hmm.
already taken in the class. Also, sir also taken in the class. And the question is any simple question.
Mm-hmm.
Uh, hmm. But there is a doubt in the answers supplied.
One
Actually, that
second.
question. Uh,
Yeah, I am opening the NPTEL lecture. 1 second. Yeah,
Assignment or
you tell
even
me assignment number two.
two, assignment number two,
Mm-hmm.
question seven.
1 second. I am logging in. Mm, अरे देवा.
And sir, already you have taken that any problem in the live session.
Okay, so like you are saying the explanation, there is some issue.
Ha ha ha.
1 second. I have not checked the released version of
Uh,
this thing,
Actually,
assignment.
sir, already I asked that in a question on a question forum, but
Uh,
nobody replied until now.
1 second. Assignment two you are talking about, right?
Ah, yeah, sir.
Okay, it is opening. Give me some time. The internet is not that fast today.
Sir, even I can explain orally. Things are
Uh,
you know that any problem.
yeah, so seventh question. A
Ha ha.
sealed rigid tank contains 1.5
Yeah,
kg
yeah,
of.
sir. Ha. Sir,
Okay.
in that any question, seven question, it's
Mm-hmm.
any okay because in this one explanation is that you have to compare the volume of the system with a, critical volume of the water. Okay. Huh. So
Mm-hmm.
if that volume suppose greater than the critical volume, in that
Mm-hmm.
answer is that there is a drop of liquid level. That is
Okay.
an correct. Okay.
Mm-hmm.
Then in a question number 8, if the
Mm-hmm.
mass of the water present in the tank is different,
Mm-hmm.
what will be the answer for will the answer for question 7 change?
Mm-hmm.
Uh, because that
So here
specific
the
volume
answer
of
is, so yeah,
the
so
yes,
then your question, like, what is your query? Can you get to that point? I saw
yes,
the.
answer provided is the S, but
Mm,
it should be the may or may not.
correct. Or
That
it
is
can
my
be,
that
it
is
can
my
also be.
thinking. I
Mm,
may wrong that, but my explanation is that one the volume that is volume is calculated by
mm,
total volume divided by the mass. If
correct. That
the
is correct.
for any value of the mass
Mm,
that will not any change. If the mass is suppose after calculate for some values, if the mass
mm,
is more than the given mass 1.5, which is given in the question 7. So
Hmm.
definitely in that any case, volume will any decrease. If the volume
Hmm.
will any decrease, then it is a less than the critical volume. Then in
Hmm.
that case, that there is a rise of the liquid
Level.
level.
Correct.
But if the volume mass is suppose, say for example, suppose 1 suppose, in that case
Hmm.
specific volume will become the 0.06. Again, it is a greater than the critical volume. In that
Hmm.
case, answer will remain the same. It will not change.
Correct. Correct. I think the question was meant to ask the second case. See, question number
हाँ,
7. It
हम्म,
is describing when your specific volume is greater than
हाँ,
critical specific volume.
critical, yes sir.
Uh, so in that case, whatever question 7 is telling, that is true.
It
But
is correct sir.
I
हाँ,
think frame by while framing question number 8,
हम्म,
what you are saying is true. If the changed mass or the mass of water which is different, if it
different.
is less than V critical, then there will be another solution. And if it is still higher than V critical, then the same
हाँ,
solution as 7
yeah,
number.
yes.
So yeah, I think you are right. But I think the 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 thing is, I think the question setter also had different thing in his mind. But while writing, he or she should have mentioned in bracket that when the specific volume is lower than the V critical. Because if not, then the answer will be same as question 7, right? So yeah, I think C is a better option for a correct answer. But what I'll do, I'll write to the uh, person who is handling this assignment section, uh, and I'll highlight this thing. And if he or she agrees with me, then it will change. But as far as I am concerned, the question is incomplete. It should have been more
हाँ,
explanatory.
हम्म,
And if it would have been more clear as to what the
हम्म,
question is asking, I think you can get answer A as well and C as well. So,
yes sir. हाँ,
yeah, I understood your point. Your point is well taken and good. That means you are following assignments and solutions as well. That's good. So keep on doing the same. And if you find something off while I am explaining, you can point out that also. No
हम्म,
worries. I think we have one more student, Roshan. But anyway, we are at 6:10. So what I'll do,
better, हाँ,
uh,
yes sir.
I'll start with the next week discussion because
Okay,
otherwise we'll
okay.
be extending again.
Hmm.
So that is not good for anyone. So anyway, as you may have seen, the structure of this class is I'll not focus solely on the problem solving approach because that in any case you have seen in class because Professor Chakraborty is also taking number of problems, Professor Bandapadhyay also taking number of problems, and after that Abhik is also taking relevant queries and problems from the assignments. So I don't think only if I take only problems that will be much of an knowledge addition to you. So instead, what I'll do, I'll briefly explain what all the topics that were covered in the last week, and I hope that you have gone through the lectures. If not, you might have seen. Narendra, can you mute yourself?
Okay,
Background
okay
noise
sir.
is coming. Uh, okay, thank you. So yeah, first is I think the main very important topic that we saw in week 3 is uh, work and energy. So I mean this looks like a trivial concept, but for this course in which you are studying basic concepts of thermodynamics, these are the I would say building blocks for your course going forward. So it's better to just look at this for a little bit again, and I'll try to explain different traps that are set in the competitive exam or in interviews. I have seen many people struggling with this type of questions only. If you go to any interview and if they ask you what is work, many a times students fumble because they had prepared all the things like first law, second law, availability, exergy, etc., etc. But if someone asks you this basic question, what is work or what is energy, at that time under pressure, students are unable to answer. So unless and until these things are very clear to you from the start, it will happen with you as well. You will also fumble, which is not a good thing. So before solving some problems, I'll just explain what all the things that you should know regarding this concept, uh, considering gate and all, competitive exams and all. So first of all, the standard definition of work. It's in all the books. PK Nag, Sontag, Shapiro. Even in the lectures, Professor Chakraborty told you and explained the definition in quite a elaborated manner. So I'll not spend much time here, but just to quickly go through it. Work is done by the system. Uh, Done by the system if uh, sole effect on the surroundings could be that of raising a weight. So this definition is quite self-explanatory. You should know the concept of system by now. You should know the concept of surroundings, and you should also know why this is could be, why it's not like exact type of connecting word. It's a possibility because raising a weight, it's just a template. You can have different effects on the surroundings depending on different types of works which were discussed in class. So some of them are like what we generally encounter in this course is mechanical work because of pressure difference. There can be shaft work, there can be flow work, there can be stretching of wire, electric work, magnetic work, etc., etc. So all those things are uh, you know uh, sum up using this raising a weight concept. So while answering any question in interview, you should just give this explanation and let the interviewer ask you what is the raising of weight. Then you can explain that these are all the types of weights that types of works that can be these are subsumed in this template. One more point that you should know is in this course, uh, like in general from mechanics, work is force into displacement, net displacement or displacement. In mechanics, you take this as an applied force, but in thermodynamics, this is resistive force. Uh, and as a consequence of this definition, if this resistive force is, let's say, I'll put RF for is just for saving time. If resistive force is zero, that means work done by the system is also zero, and this is observed in the case of uh, the type of system when you have a partition membrane, you have a compressed gas here, and you have a vacuum here. So when this partition is lifted, the gas expands, but there is no uh, no work done here. So this is because the force that we consider in the definition of work in case of thermodynamics, it is a resistive force, not an applied force. So that is one thing which is important. This will be asked to some of you, I hope, and you will be able to answer. uh, and one more thing that you should understand in this course is like that matlab, the reason why we consider most of the problems as piston cylinder assembly, you'll see, one second, you'll see the template of many problems in this course or at this point of course. It is like there will be one piston and there will be one cylinder. So the basically why we study this is and this is our system. Whatever matter is present within this confined volume, it can be air, it can be any gas, liquid, two-phase mixer, anything. So this is our system. So essentially in this class or in this assignment, what you are studying is when your system boundary is moving, What is like when your system boundary displaces, and we assume a quasi-static process or quasi-equilibrium process. For such type of case, what is the work done? And also we consider simple compressible fluid. I mean substance, not only fluid, because liquid also can be there, two-phase mixture and all. So basically, by simple compressible substance, you mean only effects of like pressure, volume, temperature are considered. The the high, the more developed effects of electrical, magnetic field, etc., etc., are not considered. It's a simple substance, and we assume it's a quasi-equilibrium or quasi-static process because in that case you can assume your resistive force equal to the pressure inside the system into the area, no, into the normal area on which it is acting. So you should remember that doing you are solving these problems which fall into this category, and these three things are there, and based on that the typical choices of piston cylinder assembly. If you go further in this course, you'll see piston cylinder assembly is not followed everywhere, and that's because these assumptions change going forward. So yeah, so that is your basic premise that you should be aware of what you are doing here. Then one more thing is, as Professor Suman Chakraborty also explained, generally when we say like the work done, or elemental work done, you can write it as dw as well. Del w is equal to pdv. I'll put this symbol for volume wherever possible, because generally we take velocity also. Some people follow other convention, but I'll try to follow this convention as much as possible. Sometimes I'll just write v when there is no velocity involved, so don't get confused if you see v or this type of symbol. So anyway, so many a times people say this is only for closed system work definition, but that's not true always. It is typically true for a closed system because the piston cylinder assembly, there is no exchange of mass with the surrounding. So it is a closed system. But as Professor explained, if the cylinder has a hole at the bottom, and if the mass is coming and that is causing the piston to move upwards, then also PDV can hold, and that is a special case. So don't say blanketly that this is a closed system work formula. As I told you, sorry, as I told you, these three assumptions are there. For this, we are solving the problems. Typically, it is true for closed system, but not always. That is the takeaway. Now, one simple exercise that is typically done. And one more thing before we go to the problems. You might have seen, uh, like, sorry, you might have seen uh, like these or these symbols. They are for inexact differentials, uh, which are work and energy. I'll denote it by E at this point. And when the differential is exact, that means it is a path independent differential. Then it is a property. Oh, I'm sorry. It should not be E here. It should be heat, and here it should be the energy of the system. Professor also explained in the class that from taking two processes, 1 to 2, if you go to the from 1 to 2 and while coming back, if you take two different paths, the difference of work and heat are same. So this quantity, which is energy of the system, which is difference of work and heat in this case for such system. So for them we use exact differentials, and they are property of the system, and these are not property. And one sign convention is also important that we generally follow. uh, so if work is done by the system, it is positive. If it is done on the system, it is negative. So some of you might be seeing this for the first time, so it is difficult because the sign convention of heat is exactly opposite to this. So how do you remember this? You can follow your own ways, but what I follow for me is I treat work done by system as an equivalent to exercise by me. So if I do exercise, then it is good for me, that is positive. If I don't do exercise, I'll be not healthy, and that is negative. So I compare work done by the system as, doing exercise. And for heat, the analogy that I use is heat, I treat it as money. If someone gives you money, that is good. If someone takes money from you, that is bad. So similarly, if someone takes heat from the system, that is negative. Someone gives heat to the system, then it is positive. But these analogies work for me. Over the period of time, I have been comfortable with these analogies. You can follow your own, but the point of the story is you should remember when the work is positive and when the work is negative, and vice versa for heat. So yeah, after that, again, one simple exercise that you may need is, if, let's say, if your work is PDV work, and your system, the piston cylinder assembly, or I'll just write system here because it is shorter version. System follows the process, let's say PV power n equal to any constant, arbitrary constant C. So this is, as you may know, it's a polytropic process, and if n is equal to 1, this is isothermal. If n is equal to gamma, then it's adiabatic process. And there are the two cases when n is equal to 0, then P equal to C, isochoric or constant pressure process. When n tends to infinity, it becomes isobaric process. Uh, so yeah, and to derive the work, you just basically integrate this system, this
Sir,
equation.
sir, hello, sir.
Ah,
So
tell me.
I think, sir, when n equal to the zero, then
Mm-hmm.
it is a isobaric process,
Oh,
and
okay,
n
okay.
equal to the infinity, then it is a constant volume,
Yeah, yeah,
isochoric.
sorry. Yeah, sorry,
Uh,
sorry. While
yeah,
writing, I confused.
yeah, sir.
It's isobaric and it's isochoric. So basically, when n equal to 0, this V power n terms goes to 1. So P equal to C, it is a constant pressure process or isobaric. And when n tends to infinity, so basically, uh, your volume power is, like, the term volume is very dominant compared to the pressure term. So basically, it's a constant volume process, which is isochoric. So yeah, coming back to this derivation, it's a simple derivation, but you should remember some things here. First of all, you cannot write this as W2 minus W1. It's totally wrong. You should write W1 to 2 or W1 to. Many people write this type of notation, and depending on your system process, you can put that equation, put the value of P from this equation to here, integration equation. So basically, you'll have C dV and V to the power n here. So if this is the case, then you can do simple integration, and then in the end, you can replace C with P V power n. So that is a simple derivation you can do. It was done already, I think, in class, so I'll not go there because then the time will be not sufficient. But I'll give you one hint which can be useful for you in the competitive exam. So generally people write 1 to 2, 2 to 3, 3 to 4. So sometimes that becomes confusing. So what I do is I write initial to final. So anything, if it is 1 to 2, my initial state is 1, final is 2. And then I write it this way, uh, P final, V final minus P initial, V initial divided by 1 minus n. So by this logic, you will not get confused as is it 1 to 2, 2 to 3, 3 to 1, 4 to 5. Whatever it is for a process, you just look at your initial state and put that pressure and volume values here in this term, second term, and whatever your final pressure and volumes are there, put it here, and then you can divide it by 1 minus n. So this trick comes in handy for many competitive exam problems because they test this type of concepts only there that you should be aware of. And yeah, one more thing I wanted to tell you before moving to the problems. That different processes that we showed you here, maybe this will be discussed again later somewhere in the course. If you plot PV plot for a particular process, let's say the process is PV power n equal to C, and this is specific volume. You can don't get confused. These are same terms here. So if your n is equal to 0, your process is, I'll say this is your initial point. Let's say you reach final point here. This is your expansion process at a constant pressure. Now this is for n equal to 0. So if you have n equal to 1, you'll have a xy equal to c type of mathematical relation for the curve, which is PV equal to c. You'll have something like this. Then this is your some final state p prime, f prime. Sorry. Now if you have n equal to gamma, which is for adiabatic process, then your line will be below the uh, you know isothermal line, which is n equal to 1. And if you are isochoric process, which is n equal n tending to infinity, let's say you reach some f triple prime. So yeah, one thing you should notice is, and this is for expansion process, basically your system is doing the work. So work initial to final, it will be positive here. Your system is doing work on the surrounding, that's why it is expanding. So net effect should be work done by system positive. You may give heat to the system, but you understand what I'm trying to say. This is an expansion process. So yeah, one key takeaway is this is an isothermal line, and this is a adiabatic line, adiabatic expansion. And while compression, it will be exactly opposite. So while compression, you will have such type of curves. While compressing, this is your initial state. This is your final. One second. This is your final, let's say f prime, and this is your f double prime. If you plot it on PV plot again, so this will be your. It will be opposite. So in this case, this will be your adiabatic process, and this will be your isothermal process. So please bear this in mind. It may be confusing sometimes, but if you practice enough, you'll get the hang of it. So, so the the takeaway of drawing these figures is the thing is, as you know, area under PV plot gives you work done. So, if you look at this first image on the left side here, so if you are doing an expansion process in which you are extracting work from the system, your system is doing the work. In this case, it is better to have isothermal expansion than adiabatic expansion, because in isothermal expansion you'll get more work done from the system, since because this area will be more under the isothermal process rather than adiabatic process. So yeah, and the reverse is true. While compressing, you should have an adiabatic. You should have also isothermal process, not the adiabatic process, because you need more work for the adiabatic process. So that is a key takeaway. It has some consequences. Maybe you'll deal with them later, not at this point in the course. But I just thought, since we are discussing PV power and here, I'll just plot them here. And yeah, I think let me just check if anything else is there. Uh, yeah, and then there is a first law of thermodynamics. Uh, So TD is a short form for thermodynamics. And bear in mind, this is for control mass system here. In this weekly assignment or in this week, it is for a control mass system. Control volume system, it will be different type of derivation or different type of expression. There are two ways to define this. One is for a cyclic process, and another is for a like simple process, like 1 to 2, like that. Not a cycle. In cycle, you return to the initial point again. So in cyclic process, essentially, since you are returning to your initial point after completing a cycle, change in your energy of the system is zero. So basically, your work interactions during that whole cycle are equal to the heat interactions. And in case of process, the first law of thermodynamics takes the following form. Work done from 1 to 2 is heat addition plus, uh, let's say, delta E, which is E2 minus E1. Since it's a property, I can write it as a exact difference. So yeah, so that is the expression. And one more key point is, if if you see the composition of this E, uh, then it has all sorts of energy. Your system has different forms of energy. Macroscopic form of energies will be kinetic energy and potential energy, which are observed on a bulk scale. Uh, and there are certain types of energies which are associated with the intermolecular level or microscopic level, we call it. So for this course, those all energies which are due to different degrees of vibrations or degrees of freedoms of molecules or atoms, they are grouped together in the form of internal energy, which is denoted by U. KEP, for typical examples that you see in this course or in this type of systems, control mass systems, these are negligible relative to the changes in internal energy. Therefore, we generally don't consider them, but they are there, and they may become relevant or non-negligible for control volume systems in certain cases. So it's not outrightly zero. Sometimes it is okay to assume them zero, but not always. You should remember this. This is not always zero. So yeah, and then you know there is a definition of enthalpy. Uh, then there is a definition of CPCV, and CPCV minus or the difference of CPCV is equal to R. But those things I'll think they'll be more relevant in upcoming sessions, so we'll not spend more time there. One more thing is what Sir also explained. If you are considering your system is made up of ideal gas, then your CPCV will be function of T, temperature in Kelvin or whatever unit. But if it is a calorically perfect gas, your CPCV will be constants. They will not be a function of temperature. So, I mean, this type of question is asked a lot of times in interviews. Perfect gas versus ideal gas. So, what is the difference? So, basically, perfect gas is a special case of ideal gas for which Cp, Cv are not functions of temperature. If you explain this much, don't know this difference and they struggle a lot. I myself did not know initially, but then I learned about it gradually. So yeah, I think these are all the major topics that you should be, available. Sorry, you should be aware of, not available. So now we'll go to some problems. I think most of the problems are solved already for you. So what I'll do, I'll just write or solve those problems which I feel are very important from this area. First of all, one thing you should know, like work and energy, work and heat, they are inexact differentials. So that is there, which means they are not a property. Sorry, 1 second. Not a property of the system. You should know this. Second, there is this is, and one more difference is they are energy in transit or transient. People use different words, but we can see it can be a transit. So basically, you'll see work and heat only if there is a movement of system boundary in this case, or there is some sort of transient condition in the system. If your system is having, let's say, it's an isolated system, it has no mass and energy interaction with the surroundings, then there is, you know, you can't define work and heat there. So they are in energy in transit. That is one important thing. And like when the system is not in transit, then the energy content of the system is given by the energy, which is E, or internal energy U. So you should know this. And since they are energy in transit, they are 1 second. They are a boundary phenomena. So you should know these 2 3 things about work and heat. If you know this, I think you're good to go. So some, one sentence type of questions are like this only. You will be able to solve them easily. Uh, hmm. And like, let me just define the heat, which is typically given by symbol Q in this course. Uh, it's defined as energy transfer or energy interaction. You should write energy interaction between system and surroundings due to virtue of temperature difference. So if some of you, which is delta T, if some of you have taken heat transfer course or maybe taking in future, you'll see this temperature difference is the driving force behind heat transfer. If there is no temperature difference across a system boundary, there is no need for heat interaction. Heat interaction cannot happen. So you should know this, that your delta T is very important. Without it, you can't do any heat interaction. And all other forms of energy interactions between system and surrounding, which are not due to temperature difference, you can club them into work. So that's how you can also define work in another way. Yeah, so we have decided one more thing. If they are not a property, they are a path function. If they are a property, they'll be point functions. So this I think you learned in the previous week only. So that is understood. Now, there is. I'm just seeing like which type of problem we can take. Uh, Actually, from this area, this heat and work, mostly conceptual problems will come. But since there are some type of numericals also that can also come. So one thing is, like, as I told you, I mean, here only I'm seeing one problem where we already discussed this plot, in which you know that work done, like let's say during expansion of the system, work done obtained during isothermal process will be higher than the work done obtained during adiabatic process, provided that initial and final conditions are same. So one question I'm seeing here, it's same only, right? which type of which type of process will give you higher work. So we have already discussed this. And if you remember, according to this PV plot as shown here in my presentation, such type of questions will be very easy for you to solve. You will not struggle much. Some people tend to do mathematical derivation of PV equal to n, PV power n equal to c and all, and then they take a derivative and study the slope of the system and all, slope of the process. You can do that way. It's nothing wrong with it, but it's just mathematical exercise. If you know the concept, you can do on your own, like without going to maths. But let's say you want to do maths, then one thing you can do is, let's say you have PV power n equal to c. Before going on, let me just go back to this notation. For this class, I'll just write v equal to volume. So what you can do is, since this is a constant, you take derivative on both sides. So derivative of a constant is 0, we all know. So this term is 0. So now you use chain rule, and you do the differentiation. So having you'll be getting with the and there will be one dv. So you'll be getting this expression. This is the power -1. And then if you rearrange terms, essentially when you are looking at a PV plot, the slope will be by dp by dv. So you can get this from this expression. If you rearrange terms, what will be ending? It will be n p v power n minus 1 divided by v power n. So it will be np by v. Correct. One minus sign will be there since we are taking it on the 0 side. So now you can uh, see eh, those for like those people who are comfortable with maths, they can answer such questions using this expression, which is okay. For let's say if you take n equal to 1.7, let's say, so this is anyway constant. So your slope is a function of p by v, that is negative. So as n increases, your slope decreases. So that is again what we were saying for isothermal process, n is equal to 1. But if n is equal to 1.7, your slope will be higher. So during expansion, the process will be below the isothermal line. And during compression, it will be opposite because the rate of change of pressure with respect to volume itself is negative there. So you need to consider expansion or compression that you are studying. So let's say we'll take some numerical examples also, because sometimes it's also asked in competitive exams, like in GATE, 1 mark, 2 mark questions are there from this area. Uh, One question could be, see, professor has already taken in the class some questions in which spring is there. So essentially, let me just give you a template of those type of questions. As I told you, there will be one piston and there will be one spring. It's an atmospheric pressure. So this is a linear spring. You should be, I think I told you this last class also. Linear spring is a very important term here, because if the spring is not linear, uh, the type of solutions that you'll get will change. You will not get linear type of variation. So if this type of system is there, what happens is, if let's say your system is applying pressure on this area, this is the area of piston AP. So essentially what happens is, your system, if you plot it on PV plot, because here pressure and volume are there. So let's say if no spring is there, if such thing happens, in that case, your pressure remains constant because your system is doing work against atmospheric pressure, which we consider as constant. So in that case, you will get a typical plot like this. So here there is no spring. Okay, so you'll get something like this. If it is an expansion process, if you're providing heat to the system, then your system volume will expand because the internal energy is increasing, and it will do work against the atmosphere. So the net effect will be constant pressure process. These type of one set of problems will be this, which we were doing last time. Second set of problems, they will have spring. So in that case, what happens? Your pressure becomes linear function of displacement, or delta V. Delta V is volume change. So, and since your initial volume is constant, so it becomes linear function of V. So this is a very important thing to remember going forward, because if you get such problems in competitive exam, and if you do all conventional derivation like calculate P, then calculate uh, area under the curve and all, so that process works if you are writing midterm or any subjective exam. But for a competitive exam, if you get some problem which looks like this piston cylinder assembly with spring, you should know, and like if there are no stops or anything, you should know you'll have one second, you'll have a linear variation between P and V. So what you can quickly do to save time is, you will be knowing your initial and final condition. Let's say you are here. You can use equation of line formula basically. So what you do is, uh, for equation of line passing through 2 points, so for any pressure along this line, you can write it in this form. P, here it will be F minus Vf by, oh sorry, it will be Pi only, and Vf minus Vi. So you typically know this side because initial and final. If not, there will be some hint, so that volume is thrice, pressure is double, something like that will be given, and then you can calculate P and V for any point. So if is any point lying on this line, we can calculate using this. So trust me, this saves you a lot of time in competitive exams. In normal exams, you can do the conventional way. That is fine. It is always good to do it, but sometimes it is easier to do it this way also. And just calculate. Let's say if work done is asked, you can just calculate area. This area of a trapezoid. If you don't know, uh, you should know this, but if you don't, it is a formula in which sum of parallel sides into height. So this is your height, and these are your parallel sides, which are essentially uh, Pi plus P, any point here. So, and height will be uh, V minus Vi. So if you do this for a typical problem, you'll be very easily you'll be able to solve those problems. Uh, you can, I mean, this may be not that much convincing to you, but you can solve some problems. There will be some problems in your assignments, or other than that also, just take such a system in which there is a piston and spring and work done against this spring force plus atmospheric pressure. If you do this, trust me, more or less you'll get linear variation between P and V. So that is one type. And third variation of problems in such cases is, you'll have a piston cylinder. Sorry, a second. You'll have a piston cylinder, and you'll have a piston like this. If mass of piston is there, consider it's a constant mass, so it will just be an addition to the pressure term. You From last time, I think you know how to apply equilibrium to a piston. force equilibrium. We did this in the last class. Please revise those if you have forgotten. There will be spring again. So this is like our last problem, but there will be some stops. So this system is spring plus stops. So basically, you can do many problems and then learn this, but I have done this type of thing. And what I have observed is, uh, since let's say your initial point is this is your system, and initially it is below stops. So uh, there will be two types of processes here. First, uh, till piston reaches stops, it will be same as that of the second case which we studied. So here P will vary linearly because it's the same system, but uh, which vary linearly with respect to volume. Now the second part, when piston hits stops, what happens now? When piston hits stops, it cannot go above. That's why there are stops. So essentially, your volume of the system becomes constant. So if you stop at that point, nothing will happen. Eventually, the system will lose heat and the piston will come down because of gravity. But if you keep on adding heat to the system when it hits the stops, the volume cannot increase. So what can happen? The pressure has to increase. So in that case, the process becomes isochoric or constant volume process. So on PV plot, uh, 1 second, there is not enough space here. I'll just scroll. So if you go to the PV plot here, for such system which has stops as well as spring, so, and I'm assuming uh, our initial state is below the stops, and we are adding heat to the system. Okay, so in that case, since you are adding heat to the system, uh, its internal energy will increase and it will do work on the piston, and the piston will start moving upwards. So, and since let's say this is the volume where you hit the stop, these stops are there, you hit them. So till that point, your variation will be linear and you will reach some state, let's say 2. Now you hit the stops, your volume cannot increase anymore. So only thing that will increase if you keep on adding heat is the pressure. And if that happens, your system will follow this path, which is an isochoric process. So, and you will reach final process somewhere here. And this is a very typical problem again asked in the competitive exams, that in the end they will ask you what is the, let's say, final state, pressure and volume, and what is the work done. So one thing that you can remember is, for isochoric process in a closed mass system, work done will be 0 because PdV is there and there is no dV or change in volume, so work done is 0. So don't bother about the second part of the process from 2 to F. Just calculate work done for I to 2. So your total work done will be essentially equal to, from initial state to the intermediate state 2. And how will you calculate that? I told you, you take the area of the trapezium under PV plot. So this type of problems are very typical. Here I am not going into the numerical uh, aspects of problem solving, because by this time you have seen such problems in class. Abhik has also taken some problems, so you'll not be getting much if I solve numerical problems here. So I am just giving you different templates in which the problems are asked. So you can, as soon as you see the problem, you should remember that okay, there will be linear variation, then there will be isochoric process or constant volume process. If you have this already in your mind, it will be very easy for you to solve these problems. Trust me, and this will save you a lot of time in competitive exams. Then, since we have some time, I'll take one problem. Yeah, this type of problems are very common as well, but these are not for competitive exam. These type of problems are more subjective type of problems to uh, check your knowledge of the concept. Again, we have a piston cylinder assembly. We have a piston. I'll take one sample problem from assignments only, previous assignments. Such problems are there only, lot of them for this course. So what I'll do, I'll take a simple problem and we'll discuss what type of variations can there be. So let's say, sorry, this is a piston and it is resting on stops. In earlier case, the piston was below the stops and we were adding heat. Here, the piston already rests on stops. So, and let's say here you have your system will become this, the matter enclosed in this volume. So, this is your system, and it is a two-phase. Let's just write liquid plus vapor water. It is a water mixture, and I'll just give you a problem. Uh, Initially, the total mass is given of the system, which is 1 kg, and initial pressure, I'll put P1 for initial. Initial pressure is 200 kPa, kilopascal. Dryness fraction or quality is 15%, and it is given that piston will float if pressure becomes equal to 400 kilopascal. So why do you think it needs more pressure? Because piston has its own mass. So to overcome that m into g, mass into gravity force, you need additional 200 kPa. So if you want to calculate the mass of the piston, again you can do from here, but for that you'll need area of piston, which is not given in this problem because that is not asked. If you have area, then you can do the force balance of the piston and you can get the mass of piston also. But let's not go there. That is one type of problem we did. I think we did that last time. So now, now the question is, this system is heated slowly. I mean, this slowly indicates it's a quasi static process. It's a hint in problem itself. Till it becomes saturated vapor. So initially it was a two-phase mixture. Now it has become saturated vapor. So now the question is to find is total work done in this process. So they have not mentioned that what is the final pressure and anything. Nothing like that is given. Initial conditions are given, and they have asked. It's not known also that final pressure is more than 400 or less than 400. So you don't know whether your piston is floated or not. So you need to figure out that part. If it floats, then your volume changes. Then you need to calculate work done. If it doesn't float, then there is no volume change. Work done is zero. But in the options, I mean, if I would have been a paper setter, uh, here the options are, let's say, 53.5 kilojoule, uh, 61.5 kilojoule, 131.5 kilojoule, and 0 kilojoule, let's say. So I would have definitely given one option as 0, because in that case you had to find out whether the piston lifted off or not. If all the options are non-zero, that means your piston lifted off and there is some volume change and therefore there is some work done. But if I give you 0 also in the answer, then you can't guess. You have to solve it properly. So let's go into that. So uh, see, initially it's a two-phase mixture, so you'll need to look into the steam tables to find out the specific volume, given x1 as a dryness fraction initially 15%. So what you can do is, uh, I mean, I have a steam table here, but you also can solve this problem on your own by looking at steam table. Essentially, you need to determine, uh, initial pressure is 200 kPa. So what is the specific volume given dryness fraction of uh, 0.15? So you'll go to steam table. I'll not solve the numerical jargon here. I'll just give you the way to solve it. So solution should be on this line. You'll find specific volume from the steam table by doing uh, mm, 1 second. Uh, you can use this formula also. Sorry, this will be G only, or I think there is a, you can use this formula also, whatever you feel comfortable with, and you'll get some value in meter cube per kg. To find Vf and Vg or Vfg, you have uh, you have a pressure of 200 kPa, and X is also given 0.15. If you do this, and since it's a two-phase mixture, you'll use saturation properties at 200 kPa. You'll get some specific volume. Now total mass is given as 1 kg. So you can find out the volume of the system, which will be basically M into specific volume. So you'll get some meter cube. And so let's say, mm, hmm, what you can again do is, mm, 1 second, give me 1 minute. Oh, it's already past 7. Give me 5 minutes, we'll finish. Okay. Sorry, it's getting late, but yeah, this is the final problem, so don't worry. Uh, so now what happens? Let's say if you plot this whole process on a PV plot, it's easier to plot it on PV plot. Let's say since you're starting with the two-phase mixture, you will be inside the dome. So let's say you are somewhere here on this line, where your uh, x1 was, I'll put this as 1, your x1 was 0.15, and your P1 was 200 kPa. So, and you found out your V1 using steam table. So you know this point will be somewhere inside the two-phase region. Now you start heating the system, and you heat it till it reaches it reaches saturated vapors phase. Uh, but the thing is, hmm, so your final point will be somewhere here. It will be 2, because it's a saturated vapor at the end. Now the thing is, how do you reach from 1 to 2? That is the question, and it's a very typical problem. It is always asked many times in the subjective exams. So what you can do is, uh, let's say you don't know whether the piston lifted off or not. So one way to guess is, uh, you assume that it lifted off, and till it lifts off, the process is constant volume. And once it lifts off, since there is atmospheric pressure here, it's a constant pressure process. So if you plot it here, it will be something like this. So let's say any intermediate point A. So this will be a point till your piston is not lifted off. Once it lifts off, it is doing work against atmospheric pressure, which is a constant pressure. So this will be a constant pressure process, and initially it was a constant volume process. This is after piston lift off. So if you know this, uh, and now we'll get into the numerical things. So let's say at point 2, you know, uh, P2 will be 400 kPa only, because 400 kPa is a pressure at which liftoff takes place, and since after that it will be a constant pressure process, similar to the earlier piston cylinder cases that we studied. So finally also at P2 pressure will be 400 kPa and X will be 1, since it's a saturated vapor. So if you have these values, you can calculate Vg from steam table. It will be some meter cube per kg. So this is the V2. It is same as Vg here. And then if you multiply with mass, you will get uh, volume of the system in meter cube. Mass is 1, so it will be same value, just the unit will change. Now, now the question was asked is, what is the net work done? So you can solve this problem without finding this A. This intermediate state is not required, because work done total is work done 1 to A, then work done A to 2. Since 1 to A is a constant volume process, work done is 0, and work done A to 2 is a constant pressure process, work done will be basically P V2 minus VA, but VA will be same as V1. So, and this pressure will be 400 kPa, because it is this line, horizontal line we are talking. So you have V1, V2, and you have pressure, and you can do the calculation, and you will get work done. In if you keep the unit in kilojoule, kPa, you will get the work done in kilojoule. I'll give you the answer. You can do it on your own if you want, but it should be around 131.5. Now, for those of you who are interested in finding out this A state, which was intermediate state, what you can do is, for intermediate state A, what you know, pressure at A is equal to 400 kPa. That you know, because then only the lift off happened, and it is a constant pressure after that. Specific volume at A will be equal to specific volume at 1. You have that value also. So you go to the steam table, you take 400 kPa pressure, and it will be a two-phase region only. So you go to the saturated, saturated table. Don't go to the superheated one, and you look into the saturated steam table to find dryness fraction at A. This can be one more question that can be asked in subjective paper. So yeah, if I would have been there, I would have asked this also, because then you need to solve the problem completely. You can't, escape the problem without finding A. So this is one of the case. So I think I have covered most of the problems here. So I think it's 10 minutes past the scheduled time. So I'll stop here. I'll upload this recording on the YouTube, and I'll also share the these notes with the NPTEL team, which we'll share with you. So if you have, since there are only two people now, I think there were many people in between, but Narendra and Pisha are there. If you have any problems, you can ask me. Uh,
Sir, hello, sir.
yeah, tell me.
Hello.
Yeah, yeah.
Sir, in a today's in a class, you have explained very nicely that piston
Hmm.
cylinder arrangement with a nose spring, with a
Hmm.
spring, and spring
Hmm.
with a staffs.
Hmm.
These are very suppose useful any things to solve the problem. Thank you very much, sir.
Okay. Thank you for listening, Narendra, and thank you for coming to the class. But yeah, I
Because you
think,
explain the things any separately, sir. Any. Because
yeah,
sir
because,
also solved the number of problems of this any type, but in that any problems there was the combination, and you
hmm,
explain the things separately. That's why these are, I think, any very useful.
yeah. So I think, I mean, this is one type of way to study. You
Yeah,
can
yeah.
follow.
Sir.
You can follow this in your other
I,
courses
re-
as well.
I really impressed by this way of any explanation.
Okay. Thank you for the compliment, Narendra.
Oh,
Hope this will help you in your competitive exams.
uh,
And anything from Pisha? Yeah, she has some doubt. Prisha, can you ask Prisha? Question 8. Assignment 2, question 8. Narendra also asked the same thing in the start. You are not there, I think, initially. So, I think the confusion is because of the language of the question. Uh,
yes, sir.
it is not very clearly mentioned what is the different mass. So,
Hmm.
I'll write to the person who is handling this, and
Yes.
maybe they'll change it. But if not, as far as those of who you have raised this question, please understand the question is not completely clear. So the confusion is bound to happen. And don't worry, whatever I told you or whatever a professor has told you on in the class video lecture, you follow that only. Don't get confused by that ambiguous language of the question. Okay.
Yeah, yeah.
And it's good that you are looking at the solutions also. That's a good thing. That means you are honestly studying, and keep on asking such questions, and we'll try to answer them together. Okay.
Okay. Thank you, sir.
Thank you, Narendra.
Okay.
Anybody else? I think we can stop now then. It's already 15 minutes above the time. Okay, then yeah, have a good night, and we'll see you. We'll meet after a week next Tuesday, hopefully.
Okay. Good night, sir.
Okay. Good night. Good night, everybody. Okay. Bye. I'll stop now. Okay.
Okay.